One of the simplest ways to get real opportunities is a site people remember. If your website feels stylish, fun, personal, you will stand out. So that's why we're going to learn how to create this 3D hero section that mixes interactive 3D elements and smooth scroll-based animations. For this tutorial, we only need to install Node.js and VS Code. In regards to our assets, all we need is our planet texture, one day version, one night version, and one specular cloud version. All of these are publicly available and will be in the public repo of this project. For this project, we'll be using Next.js, but the tutorial uses vanilla JavaScript with TypeScript, so anybody can follow along. So let's initialize our project with npx create next app and name our project 3D and we're going to create our own custom settings. We're going to use TypeScript. We're going to use Biome for linting. We're going to use the React compiler. We're not going to use Tailwind CSS. We're going to not use the source directory, and we're going to use both the app router and turbo pack. Also, we're going to have our alias at @/, leave it as default, and we're going to wait a bit until the project initializes. After that, we cd into our project, clear out the screen. Now we just need to install our dependencies, 3 for Three.js, GSAP for animations, and Lenis for smooth scrolling. After those dependencies are done, we're going to install Three.js types with the D flag for dev dependency. And after all of that is done, we're going to just run npm run dev, and we're going to see our Next.js default page on our localhost 3000. Before we continue, if you like this kind of content, please follow us on Dribbble and on x.com. After we are done with the initial setup, we have to also import some public assets as well. First is we're going to import our Earth textures. So the Earth texture, as I said, has the day texture, the night texture, and the specular cloud texture. And also we're going to import our fonts in the public folder. Our fonts will be Apple Garamond and Inter variable. We can delete all of these SVG files because we're not going to use them. After that, we're going to create a styles folder. In the styles folder, we're going to import several styles. One is the main page style, which outlines all of the styling for the landing page. Since we're going to only create the hero section for one page, this is the place that we're going to store all of the styles for that. And we also have the base CSS with the base style that we want, the font CSS that stores all of the information in regards to our font sizes, and the main CSS that imports all of the CSS files in one place. After we imported our public resources and our styles, we're going to modify our main layout.tsx. First, we're going to start by removing the fonts that it comes with, removing the CSS import because we're not going to use it, and also remove the Google fonts that it comes with. And we're going to replace all of that with our own fonts and imports. So first off, we're going to import our main CSS correctly here. We're going to use local fonts. We're using the inter variable font, and we're also using Apple Garamond as a variable font. And all of these are imported correctly, and we're also using the variable so that we can reference these fonts in our CSS. And we're also going to replace these font imports with the fonts that we have. Next, we have to add types to our project. So we have to create a separate folder for types. This type folder will help us create custom import types. So we're going to create custom.d.ts. And here we're going to specify that we want to import CSS as modules. And also we want GLSL files to be imported as well. This will come in handy when we start to write headers in Three.js. After that, we're going to close off everything. As you can see, our error is not visible here anymore with the CSS import. We're going to close everything off. After that, we're going to remove the global CSS, which we're not using, and also our page.module.css. And we're going to modify the page.tsx file. We're going to remove this CSS file completely because we're importing everything in our main CSS file, and clean up our markup. And just create a fragment in our case. After that, you're going to see a blank page, which means that everything worked, so we can continue on from here. Now, let's replace this fragment with the basic markup that we need for creation of the 3D effect. So we just have a simple div with the page class. We also have a section in that page, and we have a canvas inside of that hero section div. After that, we're going to use a use effect, and we're going to import that use effect as well. Here in our use effect, we're going to create our initializer, basically. So for now, we're just going to write init planet 3D. You can call it whatever. And this function will create this function later on, and we're also going to clean up the scene later on as well. And in our dependency array, we're going to remove it. So we just initialize this 3D planet on the initial mount. And let's also create the import for the initPlanet function. And this function is going to come from @components/3D and planet. And one last thing, let's remove the unnecessary import here, and we are going to make it so that this entire page is client side. So this entire page is going to be client side, but you can wrap this section itself into a separate component and make that component client side so that you're not forcing the page to be client side when it can be rendered on the server side. So after which, let's create our components folder. Components. And in that components folder, let's create a 3D folder. And in that 3D folder, let's create a file called planet.ts. This will be the main file that we're going to work on in order to create our main 3D effect. In this file, we're going to import Three.js by importing everything as 3 from 3. Then let's create our initPlanet function that takes in, well, nothing actually. It will only return scene that is a Three.js scene. But later on, we're also going to return the renderer as well so that we're able to clean up our use effect. So first, we're going to specify the canvas. The canvas that we want to get is from our page tsx file. So we want to get planet.3d in this case. So we're going to do query selector canvas and then the class of the canvas and as HTML canvas element. And after which we're going to create a scene, which is a new Three.js scene. And also we're going to return that scene as in an object, basically. Let's format and let's export the initPlanet function as default. Generally speaking, in Three.js, we need 4 things to have. One is a scene, which we already created. The second is our camera. The third is our renderer. And the fourth is the animation loop. All of these have to be present in order to at least have something on our screen. So first, let's create our perspective camera. So this perspective camera is going to be new 3.perspective camera. And the perspective camera takes 4 main arguments. One is the FOV, which is going to be pretty low because the lower the FOV is, the bigger the object seems in a Three.js scene, basically. And we have to specify the aspect ratio. And because of the fact that the scene itself is full screen, we are going to do window.innerWidth divided by window.innerHeight. And we also need to have our near and far, meaning how close the camera can see something and how far a camera can see something. This can be 0.1 and 1000 or 10,000. And we also need to set positions to this camera. So camera.position.x equals 0. So Three.js is using a different style of x, y, and z direction. Basically, x is left and right, z is forward and backwards, and y is up and down. And we're going to have the camera position slightly to the top, 0.1, and the y position will be somewhere around 19. After that, we have to add this camera to our scene, so we just do scene.add and camera. But right now, our camera is not really responsive. So later on, we're going to add a resize event. So in order to easily configure the aspect ratio and also the pixel ratio of our camera and our renderer, we're better off creating a separate object that stores those values. So width is window.width, inner width, and the height will be window.inner height. And we also need the pixel ratio, which will be window.pixel ratio. Basically, these values are going to be updated on our resize event. And generally speaking, if we store these values like this, it will be much easier to update them later on. So in here, we're going to do size.width, and we're also going to do size.height. We're going to specify the pixel ratio in our renderer. So let's create a renderer. And this renderer is going to be new 3.webgl render. There's a lot of renderers, generally speaking. A very popular one is WebGPU, but right now we're going to just use the WebGL renderer. And WebGL needs its parameters. One of the parameters is the canvas, which we defined it here. And another one of its parameters is whether or not we want anti-alias, which we should set to true. Let's format. And for the renderer, we need to set the size. So set size. The size is basically how high and wide we want the renderer to be. So we're just going to take it from our size const. So the first argument is the width, and the second argument is the size.height. And we also need to give it the pixel ratio. So we have to do render.set pixel ratio, and this will be the size.pixel ratio. Next, we are going to tell our renderer that we want the background basically be transparent. This will be important because with the set clear color, we will be able to have the background of our Three.js scene transparent so that we can add any additional UI elements behind it. So we're just going to add a transparent color, which will have 0% opacity. And then we have to also specify the output color space. This is basically how we tell the renderer how accurate the color space should be. The best color space, in our case at least, is the sRGB color space. And let's format everything again. Now we have to create our animation loop function. Basically, we can either create a simple animation function that uses request animation frame, but in our case, because of the fact that we're using GSAP, we're going to do gsap.ticker.add that basically creates a function that uses request animation frame under the hood, but it's compatible with all the scroll triggers and GSAP animations that we're going to create later on. Don't forget to import GSAP because it's not by default, we haven't imported it by default. And of course, we have to do render.render, and we're going to give it our scene and our camera. Unfortunately, we're not going to see anything on our canvas still until we add our objects into the scene. So right now, let's finalize the initial setup with just gsap.ticker.lag_smooth that just improves the ticker function a little bit to prevent any type of lagging. Now that the initial Three.js scene setup is done, we can start creating the earth and also the interactive scrolling that happens inside of our Three.js scene. So when creating any type of objects in Three.js, you need two things. One is the geometry, and the other one is the material for that geometry. So in our case, we just need to create the earth geometry. So earth geometry that is equal to new 3.sphere geometry. And sphere geometry takes three arguments. One is the radius, which will be 2. And the second and the third argument, there's a lot more, but we're just going to use 3 arguments, is the width segments and the height segment. And we're going to do 64 on both of them. Next, we're going to create a material, but not any kind of material, a shader material that is more, how should I say, a versatile material that you can apply shaders to. So let's create earth shader, or better yet, let's call it earth material. New 3. This will be shader material. And the shader material will have two main things: vertex shaders, which will be just a regular string for now. We're going to populate it just a sec. And also a fragment shader, which will also be a empty string. And also we have to specify that we want this shader material to be transparent because of the clouds that we're going to apply on top of all the textures. So with all of that, we can create the final earth basically. So const earth is equal to new 3.mesh. And mesh takes all the things that we created just now. So the earth geometry and the earth material as well. Let's format. But unfortunately, we're not able to see anything yet. We have to populate our shader material. So if we go to our shader material and go to vertex shader, we have to define how we are going to display the vertices of this mesh. So we're not going to go in depth in how vertex shader and fragment shader works. Basically, the vertex shader is something that defines the shape of the mesh, and the fragment shader is something that is on top of the mesh, so to speak. If you want to go more in depth of how Three.js shader works and how, in general, how Three.js operates, I highly recommend Three.js Journey by Bruno Simmons. Hopefully I pronounced the name correctly. But right now we're just going to go through the code real quickly and go through some of the key elements of how we achieve this effect. So we're going to just paste in our vertex shader. And what this vertex shader does is pretty simple once you get used to it. So we're basically sharing the UVs and the normals and the positions of the mesh, and we are making sure that the mesh that we're displaying with this shader is properly displayed on our screen, considering our camera and the position of our object. And also we are creating the normals for our models, so in order for us to share it with the fragment shader. Most of the things that we're going to do is mostly in the fragment shader, so we're not going to stop on the vertex shader for too long. So in the fragment shader, we're still going to, again, paste some generic code. All of the code that we're pasting right now is more or less boilerplate for any type of shader material. These types of operations have to happen in order to have proper materials in any type of Three.js shader materials. And in our fragment shader, we're taking the normals and the UVs and the positions of our vertices from the vertex shader, and we are just giving the normals to the color of our object. Basically, we are displaying each vertex color based on where they're facing right now. So after we are done with that, we can add the earth to our scene with scene.add. And finally, when we refresh the browser, we'll see our basically earth, which will just have some normal colors that are just for presentation purposes. Now that we're kind of done on creating the initial setup for our Three.js scene, now let's start to import our textures in order to map them to our planet. In order to load any type of textures in Three.js, we need to use the Three.js texture loader. So let's create a small abbreviated variable called TL with new 3.texture loader. In this texture loader, we don't need to give it any type of arguments. In the future, you can add loader management for loading screens and such. And we're going to load all of the textures that we need for our planet. So each texture is loaded individually, the day version, the night version, and the specular cloud version. And we're also defining the color space of each texture. Again, all of this is for color accuracy. And we also need to add the anisotropy. Basically, what this does is it makes sure that the texture that we're loading is not blurry. And we also need the anisotropy. Basically, what this does, it makes sure that the texture that we're loading is not blurry and is as sharp as possible. So right now we have this shader material here, but it's very uncomfortable to write shaders like this. So we're going to install another dependency that helps us to kind of load the shaders from a separate file. In order to do that, we need to install something called raw loader. So we're going to do npm install raw loader. Can do -d flag because of the fact that this is just a dev dependency. And once that is done, we go to next.config.ts. And here we're going to specify our turbopack config, which will tell turbopack to just load in GLS files as raw strings, basically. So after that, we can go to our shader material, and instead of writing the shaders like this, we can create a folder called shaders. And in that folder, we can have earth folder. And that earth folder will have two files, one vertex.glsl and one fragment.glsl, like so. And let's close those off for a second. And if we go to our imports, we can import them, import earth vertex from shaders /earth/vertex. And we do exactly the same thing to our fragment. Just camel case it here. Remove extra imports. And if we go to our shader, we take the contents of the vertex shader from here, go to vertex here, save it, and let's format it ourselves, like so. And if we also do the same thing to the fragment shader, take it from the fragment and put it in the fragment file, we can now take those imports that we did and put it here. So in fragment shader, we do earth fragment. And in our vertex shader, we do earth vertex. And if we save, everything should be the same in our browser as it was. It's just a lot more easy to work with shaders when they are in separate files, and we can work on them individually. Now that we've set up our shaders, let's finalize our initial scene. So we need to have a resize event that basically takes all of the values that we have in the size variable and basically updates them. So we just create a global event listener of resize. And in this event listener, first we update the width with the window.innerWidth, and we also update height. And we also need to update the pixel ratio as well, device pixel ratio. And afterwards, we only need to also update our aspect ratio for the camera, which again is sizes width divided by sizes height, like so. We need to also update our camera matrix, so update projection matrix, like so. And we also need to set the size one more time of our renderer with size.width and size.height. And let's also update the pixel ratio, since if the device resizes, most likely the pixel ratio for the screen changes as well. And let's also start rotating our planet. So let's go to our tick function and let's write earth.rotation.y is equal to time times 0.2. So this time variable, as I said, is something that GSAP handles, and it's just the elapsed time of the loop itself. And we should see the planet still being the same. Right now, you cannot see that it's rotating because of the fact there's no distinctive texture that is showing that it's being rotated, but you can slightly see on the edges of the sphere that it is. Okay, now that that is done, let's go to our fragment shader and let's continue on with writing our shader. So after all that, let's continue working on our shader. So we have to import all the things that we've kind of connected between Three.js and our shader material. So everything that we have in the uniform, basically we need to import it in the fragment shader. So if you remember, we also shared a lot of things from the vertex shader, and we're also importing those values here. So after we've done all that, let's go through the process of creating our material. So first, let's create a vec3 color variable that will just be vec3 0.0. This means that we are creating a 3-valued color, but we're all pre-filling it with all zeros. Basically, each time you create a vec3 and you want to assign a color to it, you can assign it like this, but with just adding one value, it basically populates all 3 of them with 0.0 in this case. And if we remove the normal and just use the color here, as you can see, we're using a black color. And because of that, if we refresh our browser, we'll just see a black material. So let's start using our textures. So let's first import our day color. We're using the term color because of the fact that, yes, we are using textures here, but basically all these textures are boiling down to just being colors that we're applying to our shader. So let's add the uDay texture, and we also need to tell it how to display it. So if we give it VUV, that means that we're telling the fragment shader how the sphere looks like and how we want the texture to be wrapped around it. That's UVs basically. So if we give it all of the colors of RGB, and if we take the color variable and give it the day color, we'll see that our day color has been applied to our planet. And this is the first instance that we can see our texture basically on our planet. So let's continue on using all of our colors basically. So let's create the night color, which will be U night. The U again stands for, in this case, uniform. So that's why the abbreviation is there. And we also want specular clouds color. And this is also a texture that takes in specular. And again, VUV. Like so. Let's for now remove the color assignment because we're not going to just have a flat texture. But for demonstration purposes, if we look at, for example, the night color, we'll only see the night color applied on the planet. And if we look at the specular, same happens. We only see the specular texture that we have. So let's remove the color variable assignment here for now. And let's continue on creating our sun direction and or like orientation. And what we are going to do here is to get the dot product of the U sun direction, which is just basic coordinates of 0, 0, and 1. And we're also going to take the normal of the planet. And basically what this does is it takes the sun direction and the normals of our planet, and it gives us the difference between those. And in order to kind of show you how this looks like, let's apply this as our color. So let's take the sun orientation as vec3. And if we refresh, you'll see a sort of gradient, let's say, that represents a point in space and the difference between that point and the normals of our planet. So we're going to use this texture and the values it has in order to kind of fade in our two textures, our day and night textures, and everything in between. So let's remove this sun direction. So first we want to create the day mix, which is mixed between the day color and also the sun orientation. So right now, the texture that we have right now and or shader is really abrupt. So we need to kind of smooth it out for our mix. And we're going to specify the edge parameters for it. So in our case, it will be minus 0.25, 0.5, and also, of course, our sun orientation. Basically, the first two values are dictating how smooth out the sun orientation vector will be. Now that we have this mix, we can basically combine the day color and the night color with the factor of the sun orientation. So wherever there's light color in the sun orientation, we'll see day, and wherever we have black color, we'll see the night. So if we take our main color variable and append it a mix, so we mix in the night color, we mix in the day color, and we are mixing by the day mix. And after we do this, we save, and if we refresh our browser, we'll see that there is both textures applied. Basically, wherever the sun orientation is, we'll see that there's day version of the texture, and wherever we have black in our sun orientation, we'll see the night colors. So let's continue on and let's start creating our clouds. For our clouds, we're also doing the same, kind of the same thing. So we want to create a cloud mix, and this will again be a smooth step of 0.5 and 1. All these values are something that was created previously, so you don't have to tinker around with it. So what we're doing is we're taking the texture that we have, and we're only taking the green channel of it. Why green? If we look at the texture that we have, the specular cloud texture, you'll see that every cloud is represented by the green color. So we want to basically extract that and only do a smooth step depending on the green color that we have. Now that we have our cloud mix, let's also kind of finalize our cloud mix. In order to make sure that our clouds are adhering to our day mix, meaning that clouds will only appear in the light version of the planet, we need to multiply that texture with the day mix. So if we take all of that and we, again, assign the color with mix, and we give it our main color, our vec3, which only has 0.1, meaning it's white, and we also apply the cloud mix. And after all that, if we save the file and refresh, we'll still not see the clouds, unfortunately. Let's debug the code and see why. Okay, so the mistake I made here is that the specular cloud color should be vec2. The reason for that is because the only colors that we want to extract from the specular cloud texture is the red color and the green color. Plus, I've unfortunately written RGB incorrectly here, but we don't need the blue channel. We only need the red channel and the green channel. So if we save and reload our browser one more time, we'll see that our cloud texture is also applied, and it also only is applied on the day side of the planet, not the night side, meaning that wherever our sun direction is, that is where the clouds are going to be visible at. Now let's create our atmosphere. Before we create our atmosphere, we kind of want to first define where do we want to show the atmosphere. We want it to have an outer glow. Basically, we want the colors to be only on the rim of the planet. So in order to do that, we need a Fresnel. So the way we create a Fresnel is we take the dot product of the view direction and also the normal of our object, and we add, I don't know, 1.0 for now. And in order to kind of visualize how this looks, let's give it to our main color variable, make it vec3 because we need RGB, so we need to populate it with vec3. So if we refresh, we'll just see a texture that is darker in the center and lighter on the edges. So basically, this is the common way of creating a Fresnel in any type of shading language. And in order to kind of control how this Fresnel looks, we can increase this last value that we have here. And if we refresh, you'll see that our black center is a little bit more faded in to the white rims. And in order to push that black center a little bit to the edges of the sphere, we can take the Fresnel and we can assign it the power off, Fresnel itself, and with 2.0. So basically we are squaring the Fresnel. And if we save this and view this, refresh our browser one more time, we'll see that our Fresnel right now has a lot larger inner black sphere, and the smoothing is still applied because of the fact that we've added 1.1 to it. And after our Fresnel is done, let's remove the color assignment. We can start creating our main atmosphere. So first we have to create a mix the way that we did for the day mix. And the way we're going to do this is kind of the same as we did for the day mix of smooth stepping first. And we're going to smooth step by minus 0.5 and also 1 again. And we're going to take the sun orientation. And basically we're, again, creating the same type of mix as we did for the cloud mix and the day mix, but this will be specifically for the atmosphere. So let's create the colors that we want for our atmosphere. So atmosphere colors. And these colors will be a mix of the colors that we've shared from Three.js. So U atmosphere, day color, and U atmosphere twilight color, sorry. And we mix it by the atmosphere mix. So basically the mix that we created for the atmosphere, which is almost similar to the day and the cloud mix, is the alpha for this particular color. Next, let's combine everything to the main color. So take the color and mix the main color with the atmosphere color. The mixture has to be also kind of masked with the Fresnel times the atmosphere day mix. Basically, this combines both of our masks, so to speak, in order to have an atmosphere that is visible on the edges of the planet, but at the same time respects the sun orientation to kind of fade in between day and night. So if we save and refresh our browser one more time, we'll see that there's a blue tint to the left-hand side where the sun orientation is, and it's not visible right now, but there's more of a darker blue color on the right-hand side where the sun orientation dot product exists. Next, let's add a bit of reflection and also some specular textures as well. So let's create a vector2 of reflection, and this will be a value of reflect. Basically, this is a pre-applied function that Three.js is giving to us, and we can give it minus sun direction. Basically, we're telling the reflection to reflect based on the sun direction and also the object normals. In order to kind of see how this looks, let's assign this to our color so that we can visually see what is happening. If we refresh, you will see that the sun direction is still applied here, and it's going from left to right. And also we're taking into account the normals of the object. Basically, we're kind of combining these two values in order to get our reflection. And we can use this reflection in order to have some reflections on our object. Next, let's create a specular, which will be a float. And this will be a minus dot product of both our reflection and our view direction. This is a common way to create specular in any type of shader. Next, we want to specify how much we want this specular to grow and shrink, basically. So we're giving it a sort of a cap of a value. Next, we're going to increase the amount of it quite significantly. Then we are going to take the specular cloud colors red channel, which if we look at it one more time, we can see that the red channel represents the sea. So we're kind of mapping the specular to only work on the sea itself, not on the parts of the texture where there's land. And now we can take all of the things that we did, and as we did previously, mix everything. So the first value, we are specifying that we want just a white value. Next, we're going to give it the atmosphere color that we want the specular to respect, and also the Fresnel. After which we can apply all of these things to our main color variable with specular plus specular color. And if we save this and refresh our browser one more time, we can see that all the textures have been applied, plus the specular and the reflection that we needed in order to have a sort of a shiny sea, let's say. We can modify the textures a little bit. We can take the day color, for example, and we can multiply it by 0.2. This will basically increase the saturation of our planet, so it kind of pops a little bit more. Next, in order to truly properly display all the colors correctly in Three.js, we can also append these 3 lines that basically appends some shader code that Three.js provides us, and make sure that all of the things that we're importing, we're coloring, are actually colored correctly to the sRGB color space. And if we refresh the browser one more time, you'll see that all of our textures are properly displayed with their proper color spaces, and all of them are fading in depending on the sun direction. And instead of having the sun direction hard-coded in our materials, we can add these lines in order to kind of control the direction of the sun. Basically, this is a Three.js spherical object where we can use pi in order to manipulate the general direction of our sun. And we're taking the coordinates of that spherical object, and we're basically copying that spherical object's coordinates to our Earth material using the value.copy method in Three.js. After we're done with the sun direction, let's create our atmosphere. Basically, this atmosphere is going to kind of give it a glow, an outside glow, that is also going to respect the sun direction that we have here. So basically, we just need to copy our Earth material. And instead of our Earth material, we'll just add atmosphere material. And we still need the vertex and the fragment shader. We're going to remove these later on, but we just need these three uniforms for now. And we just need to add this one opacity uniform here to control the overall opacity of our atmosphere. And one small distinction between the Earth material and the atmosphere material is that we're going to remove the depth rider that basically is removing the depth buffer. What this means is that we're not going to see the depth of our atmosphere. We're just going to see the outer edges of it. So basically it will be kind of behind of our planet and still be visible. So after which, let's create our Three.js geometry. So let's create basically the same thing as our Earth geometry. So instead of Earth geometry, it will be atmosphere geometry. And after that, let's create our atmosphere mesh. So we're just going to call it atmosphere, which will be exactly the same as our Earth, but instead of Earth geometry, we'll be using the atmosphere geometry. And instead of the Earth material, we'll be using the atmosphere material, like so. And let's slightly increase the scale of our atmosphere with scale.set, and let's give it a value of 1.13. And let's repeat that for all the axes, like so. So after which, let's create a group. Basically, what group is kind of self-explanatory. It groups everything to one kind of mesh, let's say. So let's create a new Three.js group. And in this group, we're going to add both the Earth and the atmosphere. And instead of appending Earth to the scene, we're going to do scene.add Earth group that will have both the Earth and the atmosphere. So we're kind of creating one element that contains two elements instead of managing both separately. So now if we save and we refresh, we're going to see a lot of mess. So basically we're seeing, again, the disabled depth buffer for the atmosphere, but basically we're going to do the exactly same thing as we did for our Earth, meaning that we're going to kind of fade in our atmosphere lights, and we're still going to respect the sun direction that we have in our scene. So let's create our shaders for our atmosphere. Let's collapse everything so we kind of get our bearings of where we are. So in shaders, create a new folder called atmosphere. And in this folder, let's copy the fragment and the vertex shader that we have in Earth and just paste in the atmosphere for. And in the vertex, again, we're not touching too much here, but in the fragment, this is where we're going to kind of create our effect. And let's import those vertex and fragment shader. So atmosphere vertex and atmosphere fragment, like so. And let's import both of these from shaders /atmosphere let's do fragment. And for the top one, let's do vertex, like so. And in our vertex shader for our atmosphere, we're not doing anything. Again, the setup that we have here is good enough. We don't need the UV since we're not doing any texture work right now on this shader, but everything else should stay the same here. And if we go to the fragment shader, now let's remove all the things that we have here since it adds a lot of noise. So basically whatever we've done for our Earth texture, we're kind of copying it here. So there's not a lot of foreign concepts that we're going to go through here. So first, as we've previously done, we're going to add a day mix. Basically, we're taking the sun orientation and smooth stepping the mix that we want, so it's a little bit more soft on the edges. Then we're taking the colors that we have from the twilight color and the atmosphere day color and mixing them by a factor of the atmosphere day mix. And we're mixing all that stuff with our original color. And we're adding the atmosphere color to our base color as well. After which we need to kind of add a alpha to our edge. So it kind of has a fade in effect to the edges. And we're going to also smooth step that edge alpha. And then we're going to create the day alpha, which respects the sun orientation, and combine both of the edge alpha and the day alpha in order to create that fade in effect that is dependent on the sun orientation. And after we have the alpha that we want to use for color, we're basically going to replace this 1.0 with our alpha. And then let's also create our uniform, not create, import our uniform of U opacity. This is the U opacity value that we've created in the Three.js material. And after we've imported that alpha, we can also manipulate the alpha of our main GL frag color by multiplying itself to the U opacity. So after that, we're not going to see anything still. Unfortunately, if we refresh our browser, we're not going to see the atmosphere. So in order to see our atmosphere, since we're using our opacity and transparency, we are going to modify the atmosphere material to also include transparency by adding transparent true. And also we need to specify how much size do we want to show of this element. And since we're just showing the front side of the element, like the exterior of everything, we can add sides, 3 dot backside, like so. And if we save and refresh our browser, we should see our atmosphere ever so slightly glowing outside of our planet. And on the night side, it also respects the sun orientation, meaning that the atmosphere color is only visible on the left-hand side. And since the atmosphere material is also dependent on the sun orientation, we should also update it based on the sun spherical. So basically, we're going to take our atmosphere material and update its uniform on the sun direction based on the sun direction that we've created with the spherical object. Now that we've finished our planet, let's go back to our main markup and let's add our HTML here. This is just a regular div with just an h1 tag, a paragraph, and a button for call to action. And with this, we can start also adding our GSAP animations. Let's first add our plugin of scroll trigger. Then we are creating a timeline for the element that we want the scroll trigger to trigger at and the position where we wanted the trigger to be. And this scrub argument is just telling GSAP how smooth the scrolling should be and the animation itself, how much is going to overshoot basically. And anticipate pin just helps us out in removing any unwanted behavior. And pin is self-explanatory. We're pinning the element until the animation is finished. So with that GSAP timeline, we can add 2 to it. And what this 2 is doing is just taking the content of hero main and it's just telling it that it will give it a blur and it will make it disappear basically after a certain time on the scroll. And after that, we're also pushing back the camera a little bit towards the user so the planet is more visible. And we're also considering mobile users as well so that the camera is properly aligned when the users are coming from mobile. And in order to make so that this animation happens properly, that the camera is at the top of the planet and then zooms out, we have to write the positions a little bit differently. So on the Y coordinate, let's give it 2.15, and on the Z coordinates, let's give it 4.5, like so. Let's save this, but let's not forget to also import scroll trigger from GSAP. So let's do that. So import scroll trigger from GSAP /dist and /scroll trigger, like so. And if we save and refresh our browser, we should see our hero section. And if we start slowly scrolling down, our contents of the hero section is getting pushed back a little bit and also getting blurred. And our planet and on camera are starting to align to our view, like so. And if we also look at that via mobile, if we scroll on mobile as well, it also smoothly animates and the planet is in view. So the ternary condition that we added kind of helps with this so that the mobile users also get the same experience as the desktop users. And at the very end, there's one small optimization that we have to do. So we've returned the scene, but we also need the renderer, which is of type 3.renderer. Well, not renderer, but WebGL renderer, like so. And at the very end of our return, we should return the scene and also the renderer. So we're doing this in order to properly clean up our use effect instead of leaving it like this. So in order to properly clean our use effects, first we have to return the scene and also the renderer from our initPlanet function, like so. And also we're going to add a return for our cleanup, which is going to just check if the renderer exists. And then if the renderer exists, we create a variable called GL, and we're going to get the context of our renderer. And after we get the context, we can get the extension, and the context name is WebGL lose context. And we're also going to lose context on there. and after which we can dispose the render. So render.dispose. And after all that, we've properly cleaned up our Three.js scene, made sure that the function itself, whatever it spawns, we're kind of cleaning up afterwards. And that is it. After writing a lot of code, we've successfully finished our 3D hero section. I really hope that you enjoyed the video, and if you did, please subscribe to the YouTube channel and have a wonderful day.